Hello, and welcome to this presentation, Understanding Frequency Response Correction. This short presentation explains the fundamentals of frequency response correction in RF test and measurement, and why frequency response correction has become increasingly important in many modern RF applications. This presentation assumes a basic understanding of how S parameters are measured and used. If you're unfamiliar with S parameters or would like a brief refresher, you might want to watch the presentation Understanding S parameters before continuing with this presentation. Let's start by explaining what we mean by frequency response correction. As you should already know, the attenuation caused by real-world objects varies by frequency. In some cases, this is actually desirable. For example, in the case of a filter that's used to stop energy at certain frequencies and/or pass energy at other frequencies. And in this case, the variation by frequency is what we want to measure. In other cases, though, this frequency-specific attenuation is undesirable and can prevent us from making an accurate measurement of our device under test. For example, when we use cables to connect to the device under test, it's important to remove or minimize any frequency-specific behavior of the cables or of any other non-DUT components. The process by which we minimize or remove this variation is called frequency response correction. And although we're often most interested in attenuation, note that the amount of phase shift experienced by a signal will also vary by frequency and can also adversely impact our measurement results. Cables are, by far, the most common component involved in frequency response correction, but there are many other sources of undesired frequency response, such as connectors, combiners, switches, mixers, attenuators, etc. Attenuation generally increases as frequency increases. That is, the higher the frequency, the greater the attenuation. At lower frequencies, attenuation may be fairly constant or level and can often be safely ignored or easily corrected. However, many modern technologies operate at or are moving towards higher frequencies. This includes things like cellular, Wi-Fi, radar, satellite, etc. And at these higher frequencies, it's no longer safe to assume a flat frequency response. This is especially problematic when testing devices or components which are used in multiple frequency ranges or different bands. Modern radio frequency technologies also use increasingly wider bandwidths, and here again this applies to cellular and Wi-Fi signals, as well as things like radar and satellite. For example, the maximum carrier bandwidth in LTE is only 20 MHz wide, but in 5G and R, each carrier can be up to 400 MHz wide. Even very gradual frequency response becomes an issue as these signals become wider. These wider signals can experience significant amplitude variations or become less flat, and this in turn degrades the quality of the overall signal. What this means is the uncorrected measurement results can become significantly less accurate for the higher frequency, wider bandwidth signals that are now common in many modern RF applications. Let's look at an example of how uncorrected frequency response can affect measurement results. Our signal generator creates a signal that is sent into the device under test, or DUT. Ideally, the signal at the DUT input would be identical to the signal produced by the signal generator output, or at least be equally attenuated across the entire signal bandwidth. If the cable has significant frequency response, this can cause the signal received at the DUT to also have significant amplitude and/or phase variations, especially for the higher frequency and wider bandwidth signals we mentioned just a moment ago. A similar situation occurs when our device under test is producing a signal which is then being measured or analyzed with a spectrum analyzer. Just as we saw in the previous slide, failing to correct for the frequency response of the cable or other components can lead to measurement errors or an inaccurate characterization of the device under test. So how do we correct this frequency response? The first step is characterizing and storing the frequency response of a given component, and this is done using a vector network analyzer, or VNA. The advantage to using a vector network analyzer is that it can measure vector quantities, that is, both the magnitude and the phase, as a function of frequency. Since the signal is passing through these components, two-port S-parameter measurements are the most common. These S-parameter measurements are then typically stored using the industry standard touchstone file format. For two-port measurements, the results would be stored in a file with the extension S2P. Once a component has been characterized in this way, these touchstone files can then be loaded into a signal generator and/or spectrum analyzer. Within the instrument, the data in this file can be used to correct for any frequency response either in the signal transmitted by a generator or received by an analyzer. Note that this correction is done at the IQ or baseband level and can be done in real time, without any additional user intervention or adjustment. Compared to manual adjustments or post-processing methods, this automatic, real-time frequency response correction provides greater ease of use and reduces the probability of user error. One of the advantages of using S-parameters for frequency response correction is that the S-parameters for individual components can be combined. This is particularly important when components are cascaded in a test setup. For example, if our test setup consists of 2 cables and a combiner, the S-parameters for these 3 components can be individually measured using a VNA. An analyzer or generator can then use these separate S2P files to calculate and apply the necessary combined frequency response correction for the entire test setup. In this example, our analyzer is now able to correct for the effects of all 3 components and make accurate measurements of the DUT's input signal. So let's summarize what we've covered. Frequency response refers to frequency-specific attenuation and/or phase shifts, and these are often caused by components in our test setup, such as cables, combiners, mixers, etc. Because the frequency response of components can change both the amplitude and the phase of signals passing through them, uncorrected frequency response can lead to inaccurate test results. This is particularly true for the types of higher frequency and wider bandwidth signals used in many modern RF communication systems. Modern spectrum analyzers and signal generators are, however, able to correct or compensate for the frequency response of components. This is most often done by using a vector network analyzer to characterize the frequency response of components in the form of complex S-parameters. And in the event that the test setup contains multiple components, the S-parameter data from the individual components can be combined to correct for the overall frequency response. This concludes our presentation, Understanding Frequency Response Correction. If you'd like to learn more about frequency response correction, or how frequency response correction is implemented in Rohde & Schwarz instruments, please see the links in the video description. Thanks for watching.